is continue on from where we left off yesterday. And we're going to start talking about some of the computational difficulties we have to think about right away with the AX equal B that we're solving in particular. Remember that we keep harping on this problem here, how to solve for that stream function. And now we have a lot of different ways to do it, right? Because at the end of the day, this is going to turn out to be some giant AX equal to B, perhaps. And so remember, there's one other thing about this, and it's the periodic boundary conditions. So, for instance, at the edges of the domain in X, they're equal. And then at the edges of the domain in Y, they are also equal. Now, here's the thing that we want to address head on. We started talking about it last time. But let's talk about how we're going to actually do this now, which is if you have this with periodic boundary conditions, and if I find a solution to this problem, let's call it psi naught, then I can always add a constant. In fact, Charles pointed out last time, there is an audience here today. Charles, for instance, is here. See, we got 4 of us. Here is something you observe. So if we start thinking about this is what we talked about last time, which is if I take this thing and I say, if I find a solution psi naught, then I can add anything like this, and it's still a solution that satisfies this at least. Remember, it's not just this that we're looking at. We're also looking at satisfying the boundary conditions. So your hope is that the boundary conditions would take away these degrees of freedom. And by the way, it does take away these two. So periodic boundary conditions say that you can't have that. So, but you still have this. You still have a constant you can pick, and you can't nail it down. The boundaries don't take care of it. The thing doesn't take care of it. So you have an infinite number of solutions. So this is problematic because if you have an infinite number of solutions, you start asking certain questions. Isn't the stream function related to physical quantities? And what does it mean to have then an infinite number of solutions, right? So this is because partly when you solve this fluid flow problem, you'd like to get, if I'm trying to model the atmosphere or flow over wing, you better figure out, I want one solution, and I want the right one. And this is telling me I have an infinite number of the stream function. But remember, the stream function is only a proxy for what you really have, which is the velocity field. The velocity field are the quantities of real physical interest. And here they are. And I do believe I wrote them down wrong in class yesterday. One of them didn't have the right minus sign. Here they are. So if I have this extra constant c tagging along, and I take derivatives to get the real physical values I need, it doesn't matter. So in other words, I might have an infinite number of solutions in the stream function because I have any c I can pick. But at the end of the day, it doesn't matter. And the reason it doesn't matter is because I take a derivative. Okay? All right. So that's at least for u and v, but wait a minute, I'm solving also for this vorticity equation. Doesn't matter there. And let's write down our vorticity equation. It's omega t plus this here. This is the vorticity dynamics, how it changes in time and space. And there's the stream function showing up there again. And what you don't want this stream function to do is bring in this arbitrary constant so you have an infinite number of solutions. But if you remember what this thing looks like, this bracket notation represents the following: psi of x omega y minus psi of y omega x. And once again, what you see here is the derivative of the stream function. So for any physical quantity that's evolving in space and time that's of interest to us, the stream function always shows up with a derivative, which means this arbitrary constant c gets wiped out. So on one hand, you can be happy. Who cares? Arbitrary constant. I don't care what it is. It doesn't matter to you what it is, because at the end of the day, when you go solve this, it disappears. Okay? But your MATLAB will care. Because your MATLAB, if we come back here, remember, we're going to turn this into AX equal to B. And what an infinite number of solutions means is that it makes A is singular. And this is what you have to think about taking care of. Okay. So, fact of the matter is, determinant A is equal to 0, which implies that you either have no solutions or infinite number of solutions. And what we have is an infinite number of solutions. So when you push the backslash, so you're going to have problems here if you start just using backslash. All right, so how do we handle this? Did you guys remember what A looked like? Probably not, but it was big. That's a good start to describe it. Yeah, A's big. And lots of zeros in it, so it's sparse. Sparse and big. Now, the actual form of it, I don't know if you guys remember. Do you remember that? -4s on the diagonal. And then 1s, 0, 1s, 0, 1, something like that. And then 1s, 0, 1s. And then there was these 1s on the corners. Anyway, who cares?
I'm sorry, is this the one where it's basically a filter?
That's right, that's right. Exactly, exactly. And this thing had 9 diagonals, that matters. But anyway, it looks something like this. Okay, you ready? You ready? This matrix, what's the determinant? It's 0. I'm going to make it not 0.
Wait, do you know it's 0 or you're...
Yeah, I know it's 0. Yeah.
Okay.
So you know it's 0 from that. You can also, the way you really check to see if matrices are going to be a problem, 2 options. What we learned in linear algebra is say, take the determinant, see if it's 0. But we have numerical round-off here. Right? So when you take a determinant of a huge matrix, you're rounding off all these numbers. You're never going to get 0. Right? So, it's not 0. It's 10 minus whatever. No. The best way to check to see if you're going to have a problem with a matrix is you can use this command here. Condition A. So this will check the condition number of a matrix. Cond A. So if this thing is big, in fact, if you check it for this matrix, this is like 10 to 15, you're in trouble. Condition of a matrix usually should be like an order 1 parameter. And this is really telling you how 0 the determinant is 0. How close to 0 is determinant 0. More than determinant 0. Right? Because you can check a determinant by doing that too. Determinant A. But this is the way you check it. Condition number. That's the more accurate way. And there are reasons for that, but I won't go into them here. So here we go. Taylor, what's your favorite number?
7.
7. So I have all these -4s. Turn that into a 7. It is no longer singular. Now you may think we just did something completely random, and we took Taylor's favorite number, and we put a 7 in there, and it seems, well, you can't just do that, can you? Sure we can. Did we care about that constant C? So once you pick that 7, then what happens is, let's come back over here. Once you pick that 7, what you really did is you nailed that constant C to something. Let's call it C bar. It's now determined. It's some number. Maybe it's 5. Maybe it's 12. Maybe it's square root 3. Maybe it's whatever it is. Who cares? Why do we not care? Because we're going to take derivatives of this. And for every single choice you make there, if you would have picked 7 in that slot, or 37, or square root 3, it doesn't matter. It picks a different constant C that we don't care about anyway. Does that make sense?
You pick -4.
So if you have -4, it's singular. Yeah, so, what was that?
-4 is an arbitrary constant like 7.
But -4 is the one that makes it singular, right? So just anything besides -4. So when you build this matrix, and this is what we're going to do in class tomorrow, we're going to build this matrix, sparse matrix. All you'd have to do is after you build the matrix, you can just simply say A11 is equal to 7. You're done. You've just solved your problem.
And you're saying that corresponds to an initial condition imposed on the stream function at the bottom
that's
square.
right. So now what you did by doing this, you've basically said, I have an infinite number of solutions, but by doing this, I've effectively imposed one constraint on it, and by imposing one more constraint on it, I pin down that constant C.
Is that constraint some initial value at the x equals 1, y equals 1 corner, or what is it?
Yeah, it's a constraint now on that one corner right there. That's the A11 spot, right? So you've broken this thing up, and you've put a constraint there. At that grid point, you said, I'm making some other thing. By the way, people can do almost arbitrary things. I didn't have to change that diagonal term. This is the easiest thing possible. And if you do the condition number now on that, totally different. You know, if I could have just gone in here, by the way, leave it as -4, pick somewhere randomly and put 37. Okay? Normally what people like to do is put it off on an edge somewhere. Right? So if you put 37 here, then you're imposing some constraint right there in that grid point, which is like if your stuff is happening there, it's like, well, that might affect things. But normally if you put it on an edge, remember we're trying to look at the dynamics in here. The idea is hopefully that the boundaries are far away. So yes, you could do that, but if you just do this, you now have a matrix that is non-singular, and now when you do the / command, it works. The only thing I wouldn't pick here, by the way, and it's, by the way, in the notes, which is stupid, but that's okay. The notes have been I have a newer version of the notes that are updated. But I said, hey, you could pick A11 to be 0. Now, if I made this 0, there's no problem. It's non-singular. But now, what do I want to do with this matrix, right? Part of what I want to do is I don't want to use /. I want to use LU decomposition. If I use L decomposition, what's going to have to do right away to do an LU decomposition of that matrix? It's going to have to flip rows around. So I'm going to have to pull out not only the L new matrices, but also that matrix that flips them around a bit, right? So I have to pull out that extra matrix to say, oh, but if I have this, I have to shuffle my, what do you call that term? What's that? My pivot is 0, so I have to switch it out, right? So that means I have to switch rows out, which means I have to also switch out my right-hand side as well. That's one extra piece of work I have to do if I put a 0 there. So it's dumb to put a 0 there. So I'm calling myself dumb.
But that's on the computer. I mean, that's more for the computer.
That's more for the computer. However, you have to bring it around. So whatever you do this right now, you're going to have to do LU and P. And you have to then take your right-hand side and multiply that P matrix, which tells you how the rows got flipped around. So that's extra computation. So that's why it's not a good idea. So don't do that. 7's perfectly nice. And in the homework, I'll tell you exactly what to put in there so we can match up our results. All right, so this is how you take care of this problem. That's it.